Okay, hello. Today's lab is about friction. Friction is a very complicated subject. The friction we're doing in these labs is the friction of clean, dry surfaces on top of each other as they slip over each other. There are other kinds of friction for things like fluids, water, air, and so on. Those are really different. This is only for clean, dry surfaces. So to begin with, we have to start talking about a totally different force called the normal force and figure out how that works. Now, the normal force is something that comes up when you start thinking about an incredibly simple situation. Suppose we have a book on a table. There it is. It's not going anywhere. It's not accelerating. It's not doing much of anything. And that means, by Newton's first law, that the sum of all the forces on it have to add up to zero. So what forces are working on this book? Well, there's certainly gravity working on it. This is, near the Earth. There's gravity happening on it. So if I draw a picture of it, here's the tabletop, here's the book, and we have a force straight downwards called the weight. And if that was the only force working on this book, it would be accelerating toward the center of the Earth at 9.8 meters per second squared, and we would have bid it farewell a while ago. What else is going on? Well, there's another force that comes from the table. This book is interacting with the table. Even though you can't see anything happening, it's going on. And the force from the table is in an upward direction, and it's called the normal force, N. And the normal force is exactly big enough to counteract the weight. So normal force happens whenever you get two surfaces touching each other. The normal force is perpendicular to the plane of the surfaces. That's actually why it's called the normal force, is it's perpendicular to this plane that these surfaces are touching each other on. And it's almost always present when two things touch each other. Okay, that's the normal force. What about friction? Well, the kind of friction model we're going to be talking about, called the Coulomb model, divides friction into two pieces. The first one is called static friction. And static friction is what you get if the surfaces are not sliding over each other. So this is what's happening to the book if it's just sitting here on the table. Now, to understand static friction, you have to just start applying a little force on one side of the book. So suppose I lean on this side of the book just a little bit, and just kind of barely making contact with it. It's not accelerating. It's not moving. Clearly, the sum of all the forces on it is still zero. So how can that be? Here we have our book sitting on the table. The book has weight downwards. It's got a normal force upwards. And now I'm putting a little tiny force with my finger on one side. And if that was all that was going on, the book would start accelerating that way. But it doesn't. And it doesn't because there's another force. This is the force of static friction. I'll put a little S on that one. And the force of static friction is a force that comes from these two surfaces touching each other. It is in whatever direction it has to be to stop slipping, and it's however big it has to be to keep that slipping from occurring. That is up to a limit. The limit of static friction is this. The magnitude of static friction is less than or equal to mu s times the magnitude of the normal force. This symbol here is a mu. That's a Greek M. It has an S on it to tell it from the next mu we're going to see. And what you notice from this is that static friction doesn't really have a fixed size. It's just however big it has to be up to this limit. If you increase n, the limit increases, it can get bigger. It's in whatever direction it has to be to keep things from slipping. Static friction is kind of a very floppy sort of force. It's whatever it needs to be. What it does not depend on are things like the area of contact. The bigger area you get doesn't make any difference. Mu s does depend on the surfaces. Different surfaces have different numbers for mu s. Something like rubber on rubber has a very high mu s, whereas something like ice on ice is much less. Steel on ice is what hockey players use, and that's very, very low mu s. Okay, so that's one version of friction, that's static friction. But eventually, if you increase this force, it does start to move. What's going on then? What's going on in that case is the other variety of friction, which is kinetic friction. And kinetic friction is what happens when the surfaces are sliding over each other. They are moving past each other. The way kinetic friction works is, there's a T in there, is that the direction of kinetic friction is to stop the slipping. It's to stop the slipping. And the magnitude of it is given by this formula. The magnitude of Fk equals mu k times n. Okay, mu k is different from mu s. That's why they have different subscripts. Usually mu k is a little bit less than mu s for the same surfaces. Notice kinetic friction is equal to this no matter what direction we are or what's going on. It's given by this expression. The things about kinetic friction that don't matter, again, the area of contact. And once again, if you make n bigger, you get bigger kinetic friction. How can you make n bigger? Well, if you make the weight bigger, n will get bigger. So if you put more weight on that book, the kinetic friction gets larger. If you want to draw it, we can say here's the table, here's our book. We have the weight downward. We have the normal force upwards. The velocity that this thing is moving in is that direction. And if the velocity is that way, then the kinetic friction is going to be to slow down and stop that slipping. Okay, so that's our model of friction. What we're going to do with the rest of this lab is set up and measure these different parameters and explore this, try playing with different surfaces and different weights. Okay, what we're going to do now is do the lab, and in this lab we will be setting up a little experiment. We will be measuring mu s and mu k for various surfaces and various values of the normal force. To do this, we're going to have to use a new piece of equipment from out of the lab kit, which is this. It looks like a little tiny fishing scale, sort of for goldfish. That's known as a Newtonometer in the trade. We put whatever force we want on the hook on the bottom, and then a spring inside tells us how big that force is. You can see the scale is calibrated in terms of N for newtons on one side, G for grams on the other. The gram scale comes from the fact that if you hang something on the lower hook, gravity will pull it down with a force of mg. The spring to hold it in place has to counteract that with the force of the same size. And by cleverly building the right scale, you wind up measuring what m is. So let's start off by just trying to calibrate the spring balance and see how that works. Okay, first thing, if I have nothing hanging on it, my spring balance measures a force of about 0.02 newtons. So we should always subtract that from whatever we get on it. To test this thing, I'm going to measure the mass of some of these washers. They're also in the kit. So let's hang one on there. And we can see that the scale is now measuring 0.18 newtons. If I subtract my 0.02, that's 0.16 newtons, or on this side, we can see that's 16 grams. And if I hang another one on here, I get 0.3 newtons minus my 0.02 is 0.28. That would give me 28 grams for two of these things. So it looks like these washers vary a little bit in mass, but they tend to be around 14 grams each. So we have to remember that, and that will give us a nice, easy to use mass we can just apply to things and use whatever we want for it. All right, so that's the spring scale, the newtonometer. In this lab, what we do is take a piece of thread, put it on the hook of the newtonometer, put the other end of the thread around the hook on the little sled, and we measure friction by dragging the sled around and measuring the force it takes to keep the sled moving at a constant speed or just not moving at all. All right, back to the physics for what we're going to be doing next. The first thing we're going to do is measure static friction between the sled and the tabletop. And static friction, again, is where things are not sliding. The diagram looks kind of like this. We have weight downwards, normal force upwards. Those two cancel as long as the thing isn't moving up or down. It's not. So N is the same size as W, opposite direction. And if it's not sliding, that means it's just sitting there. And that means the force I put on it is balanced by a static friction force. The static friction force has an upper limit, which is given by this expression, mu s times n. N is balanced by the weight, which is mg. So we wind up saying that if this thing does not move, the force we put on it, the force we measure, is going to be equal to mu s times mg right when it starts to break. If we invert that, we find out we can measure mu s by just taking the force dividing by mg. That will give us mu s. So that's what we're going to do here. Actually, the first thing I have to do is measure the mass of the sled, because we need to know that. So we'll hang that on the newtonometer. It's above the table now, and the mass measured on the newtonometer is 92 grams. If we subtract the 2 grams that are always on there, we get 90 grams for the mass of the sled. That's an easy to remember number. Okay, now we measure the static friction. And to do that, we start pulling on the newtonometer. That's applying a force to the sled. The force will increase until it starts to slide, which it will do when it gets to the maximum static friction force. So start pulling, Force is increasing, 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 and it starts sliding around a force of 0.28 newtons on the scale, or 0.26 newtons after the correction. Let's put that in the spreadsheet and see if we can figure out what mu s is. So going back to the spreadsheet, in the first column, I'm going to have a column where I'll put down surface, and we'll keep track of that. The next column is going to be a column for mass, which will be the total mass on the sled. When we put some washers on there, we'll add that in there. And the next column is going to be the force at which it starts to slide, so we'll call that force static. And the column after that will be mu static. Okay, now we fill in all these numbers on here. The first column is the surface, which is just the table. The mass is the sled by itself, which was 90 grams. And it's a good idea to keep things in kilograms here. So 90 grams is 0.090 kilograms. The force static that we got was 0.26 newtons. 0.26 newtons. And with that, we can find out what mu static is by using this formula, which is going to be equal to the static force divided by the mass and divided by g, which is 9.8 meters per second squared. Because I converted everything to kilograms, I should be able to get that. So I get mu static of 0.29, which is actually pretty low as these things go. But that's a perfectly reasonable number. These are fairly smooth things. Let's try another one and put some more mass on here. So the original one, we had a mass of 0.09 kilograms. I'm going to put on 4 washers. I want 3 washers. 3 washers at 14 grams apiece will give me 42 grams. And we'll see what happens with that. This is again with the table. The mass now is 0.09 plus 0.042, or 0.132 kilograms. We measure what the force is. We start pulling on here and see where it starts to slide. So we pull, pull, pull. It's already quite a bit beyond where the first experiment was. And okay, we'll try that again. This thing is sliding at about 0.48 newtons minus the 0.02 is 0.46 newtons. What kind of mu static do we get for that number? Let me drag down that. We get 0.355, so it's a little bit larger. Why is it different? Well, basically these friction experiments don't repeat very well. The tabletop gets a little damper or a little less damp all the time. It's a good idea to do several of them and measure the same thing. So let's try one more time. I'll put another 4 washers on here. And I get 0.38. Okay, so these are all sort of consistent numbers for mu static. They're not that bad. Another thing we can do is try different surfaces. Here we have different surface. This one is glass. Same glass as from a couple weeks ago. And we're going to try just pulling the sled on here. So I make another column. This one is glass. The mass, we're back just to the mass of the sled. What's the force on here? You'd kind of naively expect it to be a bit less because this is smoother, but let's see what happens. When I start pulling, I get a force around 0.5. And what does that give me for mu static with glass? I get 0.56. This is actually a bit worse than the table. Let's try a few washers on it, see what happens. I get 0.50. So I'm getting higher numbers with the glass. The glass friction coefficient is actually a bit higher than the table was. We have one more surface to try, which is wax paper. Put that over the glass and see what happens. Get on there. Okay. I'm back to just the sled. And the force I get is about 0.32. Wax 0.09, 0.32, and the mu-s for that one works out to be 0.36. And it's a lot less than the glass was. I encourage you to try several different surfaces, try several different weights, see if you can get consistent results on these things, and just try at least 3 surfaces and 3 different weights for each. Okay, so that's static friction. The other kind of friction is kinetic friction. That's very similar, except instead of pulling until it starts to break, what you try to do is pull so the sled slides at a constant rate. And with kinetic friction, the force you apply is, if it's moving at a constant speed, is balanced by the kinetic friction. You do the same sort of things, but now you try and keep it moving along at a steady speed and measure the force you get out of that. Again, try this with several different surfaces, several different weights. With kinetic friction, what you're doing is moving it at a constant speed. Static friction, what you're doing is pulling until it starts to move. What circumstances you do is up to you. Send me the results. Okay.